And are you in San Francisco right now, or LA, or?
Not really. I have roots in California, but I'm in Chicago.
Oh, you're in Chicago now?
Yeah,
Cool. Windy City.
yeah,
Yeah, cool. Yeah, I'm in Toronto, so like it's pretty similar. Chicago and Toronto.
yeah.
Yeah, Chicago's bigger though, of course, but it is what it is. Yeah, cool. So wait, how long have you been in Chicago? Like a couple of years now, or
Longer than that. Let's see. I came to Chicago. Well, I came to this county in 1994.
1994?
Yeah,
Oh, it's been a while.
yeah.
Cool. Guess it's a good spot, I guess. Good spot to be.
It's been a good home for me.
Cool. Yeah,
But
that's a lot.
most of my social life is on the internet, so it really doesn't matter where I am.
Right. Yeah, the benefits of online communities, right?
Yeah.
Yeah. Sweet. Um, yeah, how should I start, or should we just wait a little longer, or what do you think?
Sure, we can start.
Okay. Um, we're gonna record this. Cool. All right. Yeah, cool. All right. Yeah, hey, thanks everyone for coming on a Sunday night. It's 7:33 Eastern time here from where I'm at. Yep, right before the Monday. Thank you all for coming. We have a pretty cool topic today, presented by Anna, of course, Anna Naden. It's quantum pseudo-telepathy. Just going over the summer real quick. Cooperative games. People are not allowed to communicate. Winning 100% of the time is not possible. However, using entangled quantum computers, the probability increases up to 100% without communication. Anna will be explaining this theory and presenting the results on IBM supercomputers. Cool. Quick bio on Anna. Anna is the organizer of quantum computing with Anna. Sweet. That's pretty cool. An online community based on meetup.com. Holds a graduate degree in physics from the University of California, Davis. Nice. Pretty chill with an emphasis on quantum theory, and has been lecturing and teaching quantum topics full time for the past 4 years. Nice. Currently living in Chicago. Now she is developing quantum algorithms and quantum software. So pretty solid background. UC Davis, Roosevelt University. Cool. Wait, so do you have an MD as well?
Well, I did graduate from medical school.
You did.
I thought I wanted to be a doctor. That didn't turn out to be the case, but
Yeah.
I graduated anyway.
Cool. Is that in Mexico that you got this degree?
That was in Mexico, in Guadalajara.
Guadalajara. Cool. Sweet. Yeah, sounds good. Just to get your LinkedIn profile here, just confirm. Yeah, cool. Now just working as a physicist for the Quantum Education Center in West Australia. Cool. Yeah, all right. Yeah, Anna, take it away. It's up to you now.
Thank you for joining me tonight. I'm going to talk about the Peres-Mermin Magic Squares game. This is going to be a deep dive into quantum programming, quantum algorithms. I'll go over the theory briefly and then give some experimental results on several quantum computers. So here's my agenda for tonight: the theory, the quantum circuit, what you would get, the accuracy you would get with random guessing, the accuracy you get with the simulator, results on the quantinuum quantum computer, and the results on the IBM computer, results on other computers, and some improvements that I made last night. So basically, the game is you have two players, Alice and Bob, and they meet before the game starts. But once the game starts, they're not allowed to communicate. And the rules are there's a referee, and the referee tells Alice, okay, you're going to play on row 1 or row 2 or row 3. In this illustration, the referee said row 3. Alice is required to put down a series of -1s and +1s, and she has to make an even number of -1s. So she could have played -1, 1, -1, or 1, -1, -1, or she could have played what you see here. Bob, who might be on another galaxy, receives a column from the referee. The referee told, in this case, column 3. Bob's rules are different. He's required to play an odd number of -1s. So, for example, he could play -1, 1, 1. I'm going to move my camera over here so that I'll be more or less looking at you while I annotate. So this is Bob's move right here. And Alice and Bob don't know in advance what row or what column they're going to get. So they meet with, and to win, they have to both play the same thing on the overlapping square. So this is a winning outcome because in this lower right-hand square, Alice played a 1 and Bob played a 1. Are there any questions about how the rules of the game are? Okay. Basically, if you work it out, if they meet before the game starts and they agree on a strategy, say Alice says, okay, if I get row 3, I'm going to play -1, -1, 1. Bob says, I'm going to play -1, 1, 1. There's no strategy that wins every time. And the reason is because in the rows, you have an even number of -1s, but in the columns, you have an odd number of -1s. The sum of 3 odd numbers is an odd number. So there's no universal strategy. They can only win 8 times out of 9. This is without a quantum computer. If they have entangled quantum computers, they can meet before the game starts, prepare an entangled quantum state, and then when the game is underway and it's Alice's turn, she simply asks her computer what move to make. And the computer performs a measurement on the quantum state, 3 measurements, giving 3 answers, -1, -1, and 1 in this example. Then it's Bob's turn. Bob asked his computer what to do. His computer said -1, 1, 1. And they won the game. You can show mathematically, and I'll discuss the reasons that they'll win 100% of the time. So this is kind of mysterious. It sounds like Alice is getting something for nothing because without the computers, she was going to lose 1 time in 9. Now they win, cooperatively win every time. So what's the resolution? How can Alice get something for nothing? Are there any, does anyone have an answer? Well, the answer is, without quantum computers, Alice can decide what she's going to play. And so she decides that she's going to play a 1. And then Bob plays. And if he wins the game, if they win, he played a 1 also. So Alice can send information to Bob. With quantum computers, Alice doesn't get to choose what she does. The computer decides for her. And this is the basis of the quantum advantage, that they win 100% of the time. So they have to prepare their computers in a state, and they use the singlet state, which is 4 spin 1/2 particles, and each pair, one going to Alice and one going to Bob, has a total spin of 0. So it's a superposition of all possible spin states. This is called a singlet state for historical reasons, because if you place these particles in a magnetic field, shine light on them, look at the emitted and absorbed light, you get one spectral line, and so that's called a singlet state. If their spins weren't opposite one another, say both of them were pointing in the same direction, that would be a spin 1 state, and the spectral line would split into 3 parts. Now, you don't need to understand that to understand the quantum computing. I just mention it for historical reasons, why it's called the singlet state. This is an entangled state. It's the famous Bell state, put out by John Bell in 1964 to explain the Einstein-Podolsky-Rosen paradox, to resolve that paradox. So ever since then, it's been known as the Bell state, the Bell singlet state. So here's how it actually works.
Sorry.
Observables.
And I just had a quick question.
Yeah.
So like you mentioned that because of the quantum computers, the two players don't need to communicate, yet they still win 100% of the time, right?
Right.
So, so like, is the quantum computer facilitating the communication between the two players?
No,
No.
there's no communication.
Okay.
They could be on different galaxies.
So the two players are both using the computers, right? Like the quantum computers.
Mm-hmm.
So, but then the computers must be communicating with each other if the computer is giving the decisions to your player, then, no?
No, the computers are not communicating with each other. If you look at the circuit, this is Alice's computer. It's operating only on Alice's 2 qubits. This is Bob's computer. It's operating on the 3rd and 4th qubits, Bob's qubits. But Alice's computer doesn't see Bob's qubits. Bob's computer doesn't see Alice's qubits.
So what causes it to like cooperate and win the game together? Because there's no is it the entanglement process that's doing that?
Yes.
Yes. Okay. So it's like there's like a quantum like connection then, but like it's not, because it's two separate circuits at the same time.
There's a connection, but it doesn't allow Alice to signal Bob.
It doesn't allow Alice to go right.
It's a little bit like teleportation,
Right.
where Bob gets a quantum state, but until he receives a radio signal from Alice, he can't reconstruct the state that was transmitted to him, so he doesn't have any information. Here's the quantum state, and you can see down is paired with up and up is paired with down, and that's the relationship that produces the correlation between Alice's move and Bob's move.
That's crazy.
Yeah.
Yeah.
Spooky.
Wait, but then But then is it the decisions of the player that's reflected on the computer, or is it decided by the computer already to make the decision for the player?
The computer makes the decision, and simply Alice and Bob simply make the move that the computer tells them to.
True. So if the player did not choose to make the decision, then like the computer would not win 100% of the time, right?
Right.
Right. So they have to, so they, okay, right. So they have to both choose what the computer gives them for them to win 100% of the time.
Uh-huh.
Okay. Sorry. Yeah. Continue. That was cool.
So these are the measurements performed by the two computers. Alice and Bob's computers each see the same measurements. The first measurement performed by Alice's computer or Bob's, the first measurement performed by either computer measures the component of spin of the first particle, Alice's first particle, along the x-axis. And it doesn't do anything to the second particle. The second measurement ignores the first particle and measures the component of spin along the x-axis for the second particle. In Alice's third measurement, she measures the x component along both axes. Now, this is the case where the referee told Alice to play on row 1. If the referee said row 2, her computer would perform different measurements, or row 3. Likewise, for Bob, if Bob was told to fill column 1, these are the measurements his computer would perform. These are the ones for row 2. These are the ones for row 3. Now, the result of a quantum measurement is an eigenvalue of the observable. That's the rule of quantum mechanics. So the product of Alice's 3 measurements is the eigenvalue of the product of these 3 operators. And so you've got x here, identity here, which doesn't do anything, and x here, so you've got x squared. Well, if you take this matrix and you square it, you get the identity. And what this says is that the product of Alice's moves have to come out to 1. That is, she has to play an even number of negative ones. Now, if you multiply the matrices in a column, you get -1. And that says that Bob has to play, for example, -1, -1, and -1, giving a negative product. So this is how it works. And because of the fact that Alice's qubits and Bob's qubits are entangled with one another, when Bob performs his measurement on the overlapping square, he gets the same result that Alice gets when she performs her measurement on the overlapping square. That's why they can win every time. Are there any questions or comments?
Yeah, Michael Ward had a question.
Go ahead.
Hi. So from my understanding, the qubits are out of multiple quantum states. Is this kind of like a quaternion rotation where the measurement is based on some like eigenvalue of these products?
The measurement is definitely based on eigenvalues. I don't use quaternions. Quaternions are definitely related. These are the generators of rotations in the special unitary group in 2 dimensions.
Yeah, because it's a rotational matrix, and the quaternion is essentially just 3 dimensions of rotation. It's very good for like tetrahedra in space. But I was just wondering, because it's if X is like a rotational tensor product, it is a tensor product.
It is right here. And you could probably do this analysis with quaternions. I just didn't.
And also, because you can get the one probability, I'm trying to get the one probability. Can you get like is there another state where it's not one, where it's slightly more than 8/9, but not one, or is it only one?
I think it's just one
Yeah, okay.
if they use these observables, because um, the product of these three operators has an eigenvalue +1.
And this is because they have no information, so it's like a Nash zero-sum game. Nash equilibrium, that kind of.
I'm not sure. I never did grasp the Nash equilibrium, but there is a discussion about it in Wikipedia, but I don't know what it says.
And I had a quick question as well. So, like, if it was a traditional like computer that the two players are using, they would just use probability to predict each other's moves, right?
Yeah, I simulated the game with a traditional computer and tried all possible strategies, and they only won 8 times out of 9.
Right. So the difference here is the entanglement process that leads to the 100% outcome rather than the 8/9, which
Right.
is right. Okay. That's the importance here. Okay. And this is what, okay.
And it relates to the fact that Alice can't choose what moves she makes. If she could choose, then she would be signaling to Bob and she wouldn't win 100% of the time. She's giving up that power of choice, giving it to the computer. And that's what makes it possible, I believe.
Can I ask you a very naive question? How is this game different or far from the simple prisoner's dilemma in game theory?
Well, there's a relationship. They're both cooperative games. They have to cooperate to get the best outcome.
But they never really win. Even if they cooperate, they each give up something.
Yeah, they each go to jail for a period of time. So this
Here
is a
we
little
go.
different.
That's not a win.
There's another game, the CHSH game,
Yes.
which the players have to cooperate to win. And with entangled quantum computers, they can win 85% of the time. Without entangled computers, they win 75% of the time. So there's a slight advantage, but it's not as dramatic.
Thank you.
So these are the measurement operators. These are projection operators. This is how I constructed. I use this to write the code, my first attempt at running Alice and Bob's computations. This is a projection operator. It takes the first qubit and whatever state it's in, it transforms it to a plus state. Now, a plus state on the block sphere is on the equator at latitude 0. I'm sorry, longitude 0. It's the x-axis. It's a superposition of up and down with no phase shift. That's the plus state, also called the X state. So Alice's first measurement can take that qubit and turn it to a plus. or it can turn it to a minus. It's a random outcome. Alice's first move can be either -1 or +1, and that's what these two terms correspond to. Likewise, her second move can be either +1 or -1. But the third move is constrained by the first two moves. The first two moves determine the third move, and that's reflected by the fact that the product of these operators is 1. So I use these operators to write the quantum algorithm. But if you look at this, it's fairly simple in the first row and the first column. But if you get out to, say, the third row and the third column, it's much more complicated. And what that means is more gates in the circuit, in the quantum circuit, more noise, more errors. And in fact, you get a very low probability of the computer actually giving them a winning outcome. In an ideal computer, with no errors and no noise, they'd still win 100% of the time. But with a real computer, if you try to do the third row and the third column, the results are very poor. So what I did was I simply concentrated on the case where the referee gives Alice row 1 and Bob column 1. Here's the general circuit I came up with. These are Hadamard gates. They mix up and down, 0 and 1. These are controlled NOT gates. They produce the entanglement. So right here you have a singlet state, a Bell state. This unitary operation corresponds to this operator right here, or this one here, or this one here, depending on what row and column the referee gave. So that gives rise to this circuit here. Alice performs 3 measurements, gets 3 classical bits that tell her what moves to make. Then it's Bob's turn. Bob performs 3 measurements. Now this unitary matrix here is a change of basis. It transforms the quantum state into a basis related to the measurement outcomes. So it's like those projection operators for the measurement outcomes. After you perform the measurement, you have to undo that transformation. So this unitary is the inverse of this unitary. Then for Alice's second measurement, she has to transform to the basis consisting of those measurement outcomes, perform the measurement, undo the transformation, and then it's time for the third measurement. Are there any questions or comments?
Yeah, I had a quick question. So does Anna go, does the player 1 go first, make the decision, and then player 2 makes the decision, or are they making the decision at the same time?
Alice plays all 3 squares first, and then it's Bob's turn.
Bob's turn, okay. So after player 1 makes the play, okay, true, all right. Yeah, so my only question is okay, because the decision has already been made with the first player, right? Can't traditional computers already take that answer and just kind of just tell them that? But then the computers aren't communicating with each other, right?
Right, Alice and Bob aren't allowed to communicate.
They're not allowed to communicate. So it's literally the particle is affecting the interaction between the two individuals, and they are they literally there's no communication though at all. It's just
There's no information from Alice to Bob.
There's no, okay, true.
And
That's,
you can see it here. These are Alice's measurements. They're performed on her particles or her qubits. These are Bob's. They're performed on the other two. So there's no overlap. There's no communication between these qubits and these qubits.
yeah, that's, I don't know. It's just, yeah.
It's mysterious.
Yeah, it's pretty crazy, actually, if you think about it.
So if you take, well, first of all, I got pretty bad results. I got like winning outcomes 20% of the time or something, which is not much better than guessing. And I didn't trust these unitary operations. I mean, sure, in a quantum computer, at least in many of them, like IBM's, you can just give it a matrix and say, okay, hit the quantum state with this matrix. And as long as the matrix is unitary, it'll perform the gate operation. But I figured there might be a lot of errors and noise. So what I did was I generated combinations of primitive gates, X gates, Hadamard gates, controlled knots, swaps. I tried all possible combinations to see which combinations would produce the same result as these unitary gates. And I got answers. And so I came up with this circuit right here. Hadamard gates, Y gates, controlled knots.
We can't see it.
Sorry.
Thank you.
Thanks. So this is the circuit I came up with. Instead of having the unitary operations, I had these gates. And I verified by looking at the eigenvalues and the eigenvectors that these were equivalent to the unitary gates. And then I ran it on the simulator and I got 100% wins. So this creates the singlet state. This is what they do before the game starts when they meet and entangle their computers. This is Alice's computer deciding what to do. These are the instructions that the computer gives her, and this is Bob's. These are measurements, these dials. Now, if you code that up, and then you ask, say, IBM's software library to draw a picture of the circuit, it looks like this. And this is pretty mysterious, because if you look at here, this is qubit 4. This is one of Bob's qubits. This is one of Alice's qubits. So Bob's stuff is happening before Alice's. And so time in a quantum computation is a little mysterious. It doesn't seem to behave exactly like classical time. And I'm only beginning to kind of wrap my head around this. But I did notice that it put Bob's qubits before Alice's.
Wait, sorry. So when the quantum circuit is calculating, like when it's doing the calculations, that's crazy. So it gives Alice's decisions first, but it uses it calculates Bob's choices first before that.
I don't know. I mean, you could move this and this to the right so that it's after this point.
Okay.
So Alice doesn't see Bob's qubits, but it makes it look like she does, but
No. Yeah, she does not.
this is the circuit and she doesn't see his qubits. So maybe I was misleading. Okay. This is what you get with random guessing. Since there are 6 choices, 3 for Alice and 3 for Bob, there are 64 possible outcomes, but only 8 of them correspond to a win. So that says with random guessing, 8 of these peaks would be wins, and the other 56 would be losses, and you'd win 12.5% of the time with random guessing. On the simulator, regardless of which of the circuits I showed you use, you win more than 99.999% of the time. Now, these peaks are not all equal, and this is due to basically, I think it's the uncertainty principle. The outcomes, you have to run the computation like thousands of times and take statistics. But with a perfect computer, a simulator, every single one of those thousands of runs is a win. These are the only outcomes you get. They're all winning. Let's have a look. This is Alice's first choice, 0, which corresponds to -1, then a 1, then a -1. This is Bob's. Bob has a 0 in his first square, which matches Alice's. And Bob had 3 -1s, which is in accordance with the rules of the game. So this is a winning outcome. And if you examine each of these, they're all winning outcomes. So every one of these 8,000 trials, the players win.
So, just quick question there. But this is assuming the fact that the player takes the decision the computer offers them, right?
Absolutely.
Yeah, 100% of the time. Yeah, they are just going with what the computer is saying to do all the time.
Mm-hmm.
Right.
It's almost as if the computers were playing the game rather than Alice and Bob.
So it's like the computers are playing, but like they're not communicating with it. Just 2 separate computers, though.
Yeah, I guess they're both communicating with the referee, who examines what they do and declares a win or a loss.
It's kind of crazy, actually.
Yeah.
Yeah.
So I first ran it on IBM's computer, and this is what I got. As you can see, there are more than 8 dominant peaks. Only 8 of these are wins, probably the tallest ones. So there's a lot of losing moves that are output by the computers. And in fact, only about 1/3 of them were actually wins. So this was very discouraging and depressing. I love quantum computers and I want them to work well, and IBM's wasn't. So I got an account with Microsoft and got a free trial on another computer. This is the trapped ion machine that was originally developed by Honeywell and then spun off into a separate corporation, Quantinuum. it did a little better, 46.5%. And the reason for that is with IBM's computer or Rigetti's, with any transmon-based computer, the qubits are not all connected to one another. Some of them are connected to others and some of them are not connected. This is called topology. And basically you can't do a controlled knot where qubit 0 controls qubit 4, for example, because 0 and 4 aren't connected. With trapped ion computers, you can move the ions around. So if one ion is qubit 0 and the other ion is qubit 4, you simply use radio frequency fields and electric fields to move them until they're in proximity. Then you send in a pulse of a laser pulse, setting it into vibration, and that causes the one qubit to interact with the other qubit. So these trapped ion computers have better topology. And this is reflected by the fact that we got a little better win probability, 46.5%. I've highlighted in red some of the losing combinations, like, oh, I'm not showing my screen.
Yeah, we see it now.
Like right here, Alice plays a 0, Bob plays a 1. They don't agree, so that's a loss. All of these are losses. But some of these others are losses too, because Alice plays like an odd number of -1s here. I also ran it on the ion Q. I tried to run it on the ion Q trapped ion computer. But because Alice's qubits get measured before Bob's, the ion Q machine doesn't allow that. They say that once you perform a measurement, the experiment is over. There are no further operations. So it just rejected the program altogether. Rigetti's, it's almost the same thing. After Alice's qubit is measured, it's used in further operations, controlled knot operations. And so that's qubit reuse. And Rigetti doesn't allow that. Are there any questions or comments? So I did a little bit of analysis. I just looked at Alice's moves. Well, let's back up a little bit. There are only 32 peaks here, and there are 64 possible outcomes. So for some reason, there's one thing the computer did accurately. It excluded 32 of half of the possible outcomes. One would have to know something about the architecture of the computer to know why that happened. Now, IBM has a trial program where you can get access to better machines. You have to give them a credit card, but they credit you with several $100s worth of compute before you have to start paying. These computers, they're called Falcon processors. This one had 27 qubits. And here's the topology. So like Qubit 14 is connected to 13, 16, and 11. Qubit 7 is connected to 4, 10, and 6. Well, my circuit only has 4 qubits, 2 for Alice and 2 for Bob. So probably what it did was it put Alice here and here, and Bob here and here, or something like that. The readout error is about 3%. So we performed 6 measurements for the 6 moves of Alice and Bob. That's about an 18% accumulated error. So you can see you're not really going to get 90% accuracy. The controlled NOT gates have a 2% error. There's quite a few controlled NOT gates in this circuit. So you can see you're not going to get what you'd like. Are there any questions or comments about the Falcon processor?
I don't have a specific comment about the Falcon processor, but I just want to confirm that the best result that you've achieved at this moment has been Quantinuum at 46.5% and IBM at 32%, right?
Well, the Falcon is better.
The Falcon is better. Okay, so sorry. Yeah, you're gonna go into the Falcon results now, right?
Yep.
Okay.
76%. I was amazed. I
Wow.
got this in the middle of the night last night. 1, 2, 3, 4, 5, 6, 7, 8. These are the winning outcomes right here. You can see they're clearly dominant. These are the losing outcomes. And you just add up the probabilities. So all of these add up to 24%. All of these add up to 76%. So that did my heart good. That looked better. Now, I decided to try brute force and just create a circuit. I know what outputs I want the computer to make. So I just put together a set of gates that would produce those outputs. This is the circuit I came up with. As you can see, it's much simpler. Hadamard, controlled knot, X, what are there? 4 controlled knots, 2 Hadamards, and 1 X. It got 83.8%.
And this is comparing to the 99.9% of the simulator, right?
Right.
Right. And the 12.5% off random guessing, which is like the best method right now.
Yeah.
Okay.
Now, there's something missing here. Can anybody tell me what's missing from these outputs? Well, there are only 4. There are actually 8 winning outcomes. So my circuit, although it produces winning outcomes 84% of the time, it doesn't produce all. It only produces half of the winning outcomes. There's another problem with this circuit. Have a look at this. This violates the rules of the game. What rule does it violate?
Someone said prior info. Michael Ward said that.
I think Bob's computation, we're not separating Alice and Bob's quantum computers. I think that's the real problem.
Right. It's the same circuit, right?
This is a different circuit. This
Right.
is a simpler circuit.
Right, but you're running this. Oh, right. But then are you running? Yeah. Okay.
So that's what I have to offer tonight. I'll turn it over to the group for discussion, questions, comments. Thank you for joining me.
Well, Anna, just back on your last comment there. So I was a little unclear on the last presentation about some of the rules and becoming a little clearer now. So in your game here, you had player A do all their moves and then player B do all their moves. I thought more like your last example, player A would make a move, player B by the referee would be told to make a move, then it would go back to player A, player B. So are both of those possible, or is only one of them correct according to the rules?
The only one that's correct according to the rules is where Alice makes all three plays. And
then player B is told to make their moves?
yeah.
Okay, okay.
Someone in the chat asked why it's not 2 to the 64. The reason is there are 6 moves. Each move is a binary choice, so you get 2 to the 6 or 64. But if you, there are 9 referee choices, so you could get 9 times 64 games. But I focused on the case where the referee gives column 0, the first column, and the first row. In no case would it be 9 to the 64th power.
May I wonder if the framework that you describe here can be useful to do systematic comparison between all these quantum computers that are suggested by different companies, like to do several cases, not just the computation that you described in detail, but to pick up other interesting cases and then give some kind of score to the claimed quantum computers by different manufacturers.
Well, isn't that what I've done here?
In one case, so.
Yeah.
But I can think about so many other situations and cases that will give maybe different picture of the scores.
Right. Well, there's something called randomized benchmarking. It's based on Clifford gates. Clifford gates have the property that they can be efficiently simulated on a classical computer. And they just look at these random circuits, not just one circuit like I did, but a circuit composed of a series of random unitary operations and measure the score.
Sounds like the crux here is dealing in detail with what happens to the unitaries. Some mystery may be solved there.
Well, the unitaries are pretty well understood. It's an engineering issue that the quantum computers don't implement them very faithfully. But the theory of unitary transformations and unitary gates in quantum computing is it's laid out in the textbook in Nielsen and Chang in great detail.
There's a question in the chat.
Yeah, Alex had a question. Did you want to read that, Anna, or should I just say it? It's kind of a long one.
Just a second. Q1 is entangled. Qubit, say there's 4 qubits, 1, 2, 3, and 4. Qubit 1 is entangled with qubit 3, and qubit 2 is entangled with qubit 4. And right, 1 and 2 go to Alice, and 3 and 4 go to Bob. And there's no transfer exactly. You could think of Alice's computer maybe based on photons, and Alice's computer emits photons which pass into Bob's computer, and he has like a beam splitter and interferometer that entangles his qubits in response. So you can definitely transfer quantum states without breaking entanglement.
A thought experiment on your original circuit, the longer one, and try to draw a line through that circuit where if we had the ability to actually execute it on two separate quantum computers, where
Yeah.
the partition would be.
Sure.
So it kind of looks like there's actually the rightmost vertical bar is sort of the separation, right?
This is a separation between Alice and Bob. This is where the game begins. This is where they meet beforehand and entangle their computers, which is like agreeing on a strategy.
Well, Alice prepares all of the qubits ahead of time, right?
Well, Alice and Bob prepare them together, I guess.
Well, she prepares them and then she sends two of them to Bob before the game starts, right?
I think she prepares her two, and they're used. Yeah, she prepares her two right here,
Yeah.
and then they interact. Here you've got interaction between Alice and Bob's computer. This is Alice's, this is Bob's.
Okay, so this is good. So that's why. As I understood this, those four qubits are prepared by Alice, and then the bottom two are somehow transported to Bob's quantum computer. But you're saying that's not necessarily the case?
Yeah, I don't think it is. I think Alice's two qubits have an influence on Bob's two qubits. But it's not like teleportation where she transfers her qubits to Bob's computer.
But who does the C naught operations?
Maybe Alice's computer emits a photon that's absorbed by Bob's computer, and then the C0 operation happens. I don't know. I haven't really thought about it too much at all, in fact.
Okay, so if we look at it from the standpoint where that, the rightmost vertical bar is the separation, in a classical simulator, the entire system's state has to be transferred to Bob's computer. Correct. But if they were actual quantum computers, the only thing that needs to be transferred to Bob's computer are the two qubits or the state of the two entanglements.
Bob's computer has his two qubits. Alice's computer has her two qubits.
Okay. So in the simple set, we would just draw a line down. We would just draw a line to separate the two machines where that right vertical bar is. But you're saying there's a possibility the line would actually split between Q1, Q0 and Q1 and Q2 and Q3?
No, I don't see that.
Okay, so again, does Alice prepare all four qubits and then shares two of them with Bob, or somehow she sends information to Bob and Bob prepares Q2 and Q3.
I think it could probably be done either way because she could teleport. She could prepare all four and teleport two of them to Bob.
Yeah, I mean that's what I've always assumed when I've seen this type of thing. But now that you mention it, it seems like yeah, there might be another way to do it.
Yeah.
Okay, so that would be a different slice through this diagram.
It would change
Yeah.
this part here.
Somehow Alice has to forward the C naught, forward something to Bob so that he could do the C naught.
Bob's computer has to somehow be influenced by Alice's
Yeah. Okay.
right here and here.
Okay, but so once again, if you do it on a simulator on a classical machine, the state of the entire system has to be available to both machines. But if you do it on real quantum computers, it's only the quantum state of the shared qubits really needs to be transferred, and then the quantum magic goes along with that, or the quantum spookiness, whatever you want to call it.
Well, I mean, it depends what you mean by a simulator. If you're simulating a quantum computer, then that's one thing. If you're simulating the game classically, that's a different
Yeah,
matter.
yeah. No, I'm not talking about simulating the game classically. I'm talking about simulating the quantum machine classically.
If you simulate the quantum machine classically, you have a state vector
Right.
of dimension 16.
Yeah, and that state has to be shared by both parts of the program.
Yeah.
Yeah.
And when early on, I wrote my own quantum simulator, and I made the mistake of allowing Alice's qubits to interact with Bob's. And then Amon, who may be with us tonight, challenged me to get it working on IBM's platform. And when I did that, I was able to achieve this clean separation between Alice and Bob that you see here.
Yeah. Also, you attempted to go to a simpler circuit. It had fewer gates, but it had more qubits.
I did do one with 6 qubits. I'm not sure I presented that tonight.
Yeah, you did. It only had about half the number of gates, but I think 6 qubits. There it is.
Yep.
Okay.
One for each one for each of Alice's moves and one for each of Bob's moves. Now,
Okay.
we could get more accuracy if we could use all 27 of the Falcon machine's qubits. I simply haven't found, it's simply not understood like how to combine. Like it'd be nice to run the computation on 6 qubits, run it on another 6, and sort of average the two together to get rid of the noise. But I haven't found anything that'll tell me how to do that. And I experimented with it. I simply used a control NOT gate to attach additional qubits to Alice's qubits and ran the circuit, and it actually degraded the performance. So I don't know how to take advantage of these 27 qubits that the Falcon processor has. And if anybody has any suggestions, speak now.
Well, I've seen some presentations on noise mitigation where they use multiple qubits to basically create one virtual qubit. If that's the right word.
Yes.
I won't pretend to understand what they're doing, but
You need hundreds or thousands of these physical qubits to protect one logical qubit. But Quantinuum has done some experimentation where they perform a measurement and then reuse the qubit and process it based on the measurement outcome. So this is like error correction with only a few dozen qubits. But it doesn't apply to this type of, algorithm.
Yeah. But in any case, when they do these simple, it winds up being more gates, more circuitry that runs in front of your algorithm. So especially in IBM land, it seems like the longer your program is, the more noisy it gets because of the coherence issues and stuff. So I'm not even sure it makes sense to try to, use 4 qubits to make 1 virtual qubit. By the time you throw the extra gates in there, you might have, to make the virtual qubit, you might have added all the noise that you saved back into the problem.
Am I sharing my screen right now?
No. So in any case, this whole business of a lot of these experiments sort of allude to having multiple quantum computers. It appears that there are working algorithms. If you just use teleportation, you could probably get the job done, right?
Pardon me?
If you just use teleportation, like in your first case, if Alice did actually just prepare the four qubits and then she teleported the 2 bottom ones to Bob, that's something that can be done now, and that should, in theory, be something you're actually moving the state of a qubit to another machine. But what I haven't seen is any machines where they have any sort of mechanism to receive those qubits.
Yeah, IBM is working on multi-distributed quantum computing.
Yeah. So we'll have to wait and see what they come up with there.
Someone asked if the computers are in close proximity, do they have to be for this to work? No, they don't. They could be on different galaxies.
Has anybody tested that theory?
There's been tests of entanglement over distances, but I think it might be measured in meters rather than light years.
Next time I'm in Andromeda, I'll give it a shot.
Send me a postcard.
Put lots of postage on it. It might take a while to get there. Right. So when I was going through your examples prior, so it occurs to me basically what's happening here then is player A needs to somehow get information about their 2 states that they've chosen of the 3 over to player B. Because they've chosen 2 states, the 3rd state is known. That was the rules. You had to do so many even, so many odd. So if you know what 2 of them are, you know what the 3rd one is. And then that 3rd one then is used by player B, and they can, as long as they follow the rules, the other two basically decrease the freedom they have. They can pick as long as they meet the even odd rules.
That doesn't sound right. It sounds like you're saying that player B sees that Bob sees Alice's 3rd move and he doesn't.
Well, that's sort of by the entanglement you do though.
His computer responds in a way that's correlated with what Alice's computer did.
Right. And so if you don't want to say that's communication, you're just kind of redefining the word communication. I mean, there's basically some influence, some non-randomness there, right? Because of the entanglement, something's happening on one and it's influencing the other.
Spooky action at a distance. That's what Einstein called it.
Okay, but it's still some form of communication.
Well, Alice can't use it to send signals to Bob because she can't decide in advance what move she's going to make.
No, I understand they're not making a choice and saying, I picked one, I'm going to send one. I mean, I do understand that. But the entanglement, however the true mechanism is, I think has got to be defined as some form of communication.
Well, that may be a philosophical issue. There was comment in the chat about books. Certainly, Nielsen and Chang is encyclopedic and almost perfect and comprehensive. I discovered that there's another book by David Mermin, who invented these magic squares with Peres. He's written a book on quantum computation. And it may have some advantages over Nielsen and Chang. I don't know. It's coming in a few days. I'm going to have a look at it. I'll keep you posted.
Wait, sorry. I'm just gonna hop in there. No, it's not. They're not sharing information because entanglement will be broken once information is measured, right? Like in the particle.
By the time Bob's third measurement is performed, there's no entanglement, that's for sure.
Yeah, well, I don't know if anyone. Okay, there's one more question, but I had some questions, but no. Okay, sorry, it was not a question. Yeah, I don't know if anyone else has any more questions, but I'm just gonna ask my questions now, I guess. So yeah, first things first, my interpretation of the impact of your research today seems like quantum computing, it's like the whole process is like pretty randomized, but like it could guarantee a certain outcome, like kind of like destiny, but like obviously it's a very like small situation. It's just two players playing a game, but then the computer is 100% outcome towards a certain like what do you call that? Just gives you 100% outcome. It guarantees you an outcome if you follow the recommendations of the computer.
Well, given Alice's move, there are still two moves Bob can make.
But if the two individuals were to follow the direction of the computer, of the quantum computer, it would guarantee the outcome that it defined.
Right.
Right.
Bob's computer would give him one of two possible winning moves. Say Alice plays -1, -1, 1. Bob can play 1, -1, 1, or 1, 1, -1. So Bob has two moves. Bob's computer can give him two moves.
But then they would, whichever decision that he chose, it would give you a guaranteed outcome, right? To both.
It would give you a win. Either way, it would be
either way. Like the directions might be deviated, but at the end of the day, the outcome is still guaranteed.
Yeah.
Which
well,
is
the fact that it's a win is guaranteed.
The fact that it's a win, and the only way that the winning would not occur is if they were to go against the direction of the quantum computer.
Yes.
Yes. Okay. So that's okay. That's the impact. So my second question is, like, as the technology progresses, do you believe that the same technology can be applied for them to make this decision at the same time? because like right now, Alice makes decision one, and then Bob makes the corresponding decision after, right? Which guarantees you, that's how it works right now, the thought experiment. But in the future, like, do you believe that like if they were to just choose the same time, it would still guarantee an outcome of winning?
I think so.
Yeah.
Well, that's what I was trying to get to before, because for the interleaving, the answer I believe is yes, based on what I saw. I took your formulas last time and kind of worked through examples. And it's just, you need a lot more circuits because you have those choices that you have to make as you go along. And at the end, with the entanglement, you can still make the decision both to have one or both to have -1, depending on the path that's chosen to get there.
Alex made a remark, if explained with causality, the time of the non-decision doesn't matter because it is all predefined. Also, it is not guaranteed if you win. I think they could make the decision at the same time, but I'm not sure. Certainly when the computer is running, every step in the computation is like a microwave pulse or a laser pulse, and they are applied in sequence so that there is a time order. But whether that's intrinsic to the process, maybe not. I'm not sure. This is something for me to think about tonight.
Time order based on the rules and the referee, but I'm wondering, it probably doesn't matter who plays first.
No, it doesn't matter who plays first.
So I just had a thought, given that hybrids are, the state of the day, and given that the algorithm for the game basically you're supposed to pick the first two squares, and then once you've done that, you can compute the third square. That's a correct assumption, right?
Right. And I could have rewritten the algorithm to only
That's okay. You're gonna ask my question. So
compute the first two squares and generate the third one deterministically.
yeah, and then hand the results off to a classical calculator, and then we could see if the noise goes down.
The problem, of course, is Bob needs a quantum state, and he's not going to get the right state if Alice doesn't perform the third measurement. That's why I didn't do it that way. I couldn't see how to give
Okay.
Bob the correct quantum state.
All right. Well, that adds some more info to the understanding.
Yeah. Okay. Yeah. I have one more question.
Sure.
Also, sorry, just want to stay out there. So like, yeah, it's pretty cool. Like, so like, is this pretty much measuring like destiny? Is that what it's doing right now? Like, because it's measuring what's going to happen, what has to happen, and because you set the parameters, like it's going to determine what is meant to be, what they're going to win.
I don't know.
I don't know. That's
a philosophical question.
Yeah,
This
that's
is
crazy
the reason
stuff.
why I coded it up, was to get rid of the ambiguities associated with the English language.
Yeah, crazy stuff. Anyways, there's another question. Just gonna, yeah, you know what? Yeah, Antigona has a question real quick.
Oh, hi, thank you so much for the presentation. I asked the same question in the chat as well. I was curious, are the computers, Bob's and Alice's computers, in close proximity? And do they have to be for this to work?
No, they don't. As far as we know, entanglement works over any distance, even astronomical distances. So all evidence so far indicates that Alice and Bob could be on different galaxies.
So let's assume that then two other players are playing the same game. at the same time, would the happening of the game of the two players, let's say Mary and George playing the same game, would their game interfere with Alice's and Bob's game? And could you please explain how this works from this distance? Just keep in mind, I'm a total novice, but very curious about the whole field.
Well, it's a reasonable question. I mean, it sounds like if Alice and Bob are in different galaxies, it sounds like there's something being broadcast from Alice's location to Bob's location. And what you're asking is, could that affect Mary and George? I would say the only way that would happen is if before the game started, Alice, Bob, Mary, and George all got together in one room and entangled all four computers.
So how would that work? Like is that from a technology point of view, entangled all four computers?
How would you entangle the two computers?
Yes, and subsequently the four.
I think you'd have to have one computer would have to emit a photon, and that photon would have to be absorbed by the other computer. And then there would be various optical devices known as beam splitters, phase shifters, interferometers. And Bob's computer would have to be an optical computer based on photons.
Oh, I see. Okay. I think I see. Okay. Thank you so much.
Great question.
Thank you.
Yeah, I'm just gonna sneak in there one more time. So I guess my question is like, what's your next steps with this now? Are you going to was this just like a one-time thing? Are you going to look to develop it, maybe complicate the model a little bit, or?
I still want to take advantage of all those other 23 other qubits that the Falcon processor has. It's a theoretical question how to do that. How do you perform error correction with a couple of dozen qubits? I don't know, and I don't know where to look to get the answer, but that's what I want to do next.
Yeah. No, yeah, it's interesting to see where this goes for sure.
And if I succeed, I'll be back to present it to you all.
See. Yeah, I guess we'll be waiting for that. Yeah, cool. Did anyone have any other questions? Because Sunday, 9 o'clock, 8:53. Sure, people just wants to do a little early, maybe. Just gonna wait a little longer for a question to come up.
By the way, I'm looking for a job coding quantum computers.
True. Yeah. If anyone has any message Anna, connect me on LinkedIn.
You can find me at quantumwithanna.com.
Yeah. So yeah. I guess that's it. Thanks everybody for joining today. Pretty interesting topic, actually. Pretty cool stuff. Just maybe what we don't know what the future looks like, but it's pretty cool. Measuring, it's good stuff. Guaranteed outcomes. But yeah, thanks everyone for joining. Thanks Anna for presenting once again, and thanks